So now that we know about gases and liquids and solids, and the main differences between them are how strong the attractions are between the particles. And in gases, the particles behave independently. There's no significant attractions holding them together. In a liquid, they're closer together. They're moving a little slower, so they can start to attract. And in a solid, usually the attractions will hold the particles in position in an organized way because the attractions are usually even more effective. So if you want to go from one state of matter to another, or from one phase to another, there's a number of different ways you can do that, but each of those changes in the state of matter will involve changes in the types of attractions between the particles and the strengths of the attractions between the particles. So understanding phase changes, there's a little bit of terminology here. You might not be familiar with sublimation or deposition. Most of the rest of these you're familiar with. Melting is often referred to as fusion, which is confusing because in the nuclear chemistry chapter in General Chemistry 2, fusion means something totally different. So that's unfortunate. Vaporization means the same as evaporation, so you want to get used to that terminology. But when you're going from one phase to another, if the quantity or strength of attractions between the particles is changing, there's going to be energy associated with that. So we have to understand the basics of what happens to the energy when I affect the strengths or the quantity of the attractions that are present. So there is, this slide is the basics. If you get this wrong or if you mix this up, it's going to be making your life difficult for a long time, because if you get this backwards, then your answers to exam questions are all going to be reversed, and it's going to probably screw up a lot for you. So when you think about energy and attractions, you want to keep separate in your mind the potential energy versus the kinetic energy. Okay, so the kinetic energy has to do with how much the particles are vibrating or rotating or moving around through space. The potential energy has to do with how stable the molecules are based on how effective the attractants are holding them together and holding them in a stable way. Right? So we know that if I have attractions and things are stable, there's not much potential for that to undergo any changes. I have to put something in to make it undergo a change. Right? So what has more potential energy? A gas or a solid? What has more potential to undergo change? Something where the particles are held tightly in position, or where they're all independent and moving around? If they're already held tightly by attractions, they don't have much potential for change or for movement. Right? So the stronger attractions are always lower in potential energy. If I break attractions, I'm going to a higher potential energy state. Right? So what that means is, anytime I break attractions, it could be any attraction. It could be London forces, dipole-dipole, hydrogen bonding, ionic bonds, covalent bonds. It could be just moving an electron from a place close to the nucleus to a place farther away. It could be breaking the force of gravity. Any attraction. You break the attraction between two things, you have to put energy in. You will always increase the potential energy. Because once you break the attraction, it has the potential to come back and reform the attraction. Right? In the solid state, the particles are already close together. They're already attracting. There's nothing you can do to make it more stable, so it's not going to do anything. If you want to change a solid, you have to put energy in. You have to put energy in by heating it up and melting it if you want to break up those attractions. In a gas, the molecules are moving around. They're not really attracting. But if one molecule bumps into something and transfers some of its speed to something else, and now it's moving slower, if it does come in contact with something, it could potentially form an attraction all on its own. It has the potential to form attractions if it doesn't already have those attractions to begin with. So it's got more potential energy. So you always have an increase in energy potential energy when you break attractions. From the point of view of the system, we give that a positive sign. The system has to absorb energy to break attraction, any attraction. And that will usually be supplied from the surroundings, right? So if you want to melt a solid, you want to break some of the attractions between the particles and make them move more and slide past one another, or you want to evaporate a gas and move the particles apart completely so they're not close enough to attract anymore, you've got to put energy in to overcome those attractions. You've got to heat it up with some external energy source. So kinetic energy or motion needs to go into the particles and make them move faster. That kinetic energy will be converted into potential energy when you're breaking the attractions, which we'll talk more about here in a couple minutes. You will observe a decrease in the temperature if this happens on its own. Okay, so what that means is you work out and you start to sweat, what happens? The sweat helps to cool you down, right? Because what's happening with the water on your skin is the water is converting into a gas. It's evaporating off of your skin. The water molecules, when they're close together, they have these attractions holding them to one another, the hydrogen bonding between the water molecules. In order to break that hydrogen bonding, energy must be absorbed by the water. So if you're overheated and your skin is hot and you have a high temperature, it's because the molecules in your body are vibrating more. So if my skin is warm, the molecules are vibrating. So some of that vibration gets transferred to the water molecules and is necessary to break the hydrogen bonding between the water molecules on my skin, and that causes the water molecules to break their attraction and evaporate. Now my skin isn't vibrating as much because some of the kinetic energy that was causing that vibration, or once that vibration was expressed in the form of kinetic energy, that's now converted to potential energy. It's no longer there in the form of kinetic energy. And temperature measures only kinetic energy. So if you have a change in potential energy and there's no change in kinetic energy, there won't be a change in temperature. But usually, if you have an increase in potential energy, you have a corresponding decrease in kinetic energy because of a law of conservation of energy. So if I want to break attractions between water molecules, that potential energy will go up for the water. Usually the kinetic energy of the surroundings, which might be my arm in the case of sweat evaporating from me, the kinetic energy of the surroundings will go down, and that helps to cool me down. Right, so then if I'm forming attractions, it's the complete opposite, right, because of the law of conservation of energy. So if I have to put energy in to break an attraction, if the attraction reforms, that exact same quantity of energy comes back out and goes into the surroundings. So if I'm ever forming an attraction, no matter what type of attraction, it always releases energy into the surroundings. It might release the energy in the form of light, but often it releases the energy in the form of heat or kinetic energy. So whatever potential energy was there, the potential for the attraction to be formed, when the attraction is formed, the potential is not there anymore. That potential has now been converted into another form of energy, usually kinetic energy. So when the kinetic energy goes up, as a result of the potential energy being converted to kinetic energy and going into the surroundings, you see a temperature increase because temperature is a measure of the average kinetic energy. Okay? So that is absolutely critical, and later in the semester we're going to have a whole chapter on energy. This is the basis of that. If you don't have this down, everything's going to be confusing. So this is super critical to get the difference down between what happens when you're breaking attractions and what happens when you're forming attractions. So we can apply this to the changes in the state of matter, right? So in the solids, the attractions are present. If I want to break them, I have to put energy in. I have to break some of the attractions. No matter what it is, there's some attractions. Even if it's completely non-polar and it doesn't have any partial charges, there's still London forces because of the temporary partial charges that form when the electrons shift around. So even if I don't move the molecules apart and break all their attractions, to get them to flow and behave like a liquid, I have to break some of their attractions. And also, generally when I go from crystalline to disorganized or amorphous, which liquids are amorphous, then I have to break some of the organization. And often the organization is necessary to maximize the sites of attraction and allow a molecule to line up with other molecules and attract in as many locations as possible. So when I allow things to slide past one another, I have to break some of the attraction. So to go from a solid to a liquid, I go up in potential energy. Got to break some attractions. Go from a liquid to a gas, I have to break a lot more attractions now because the particles have to completely separate. They won't have any attractions to any intermolecular attractions to one another. If I go directly from a solid to a gas, which is sublimation, the amount of potential energy increase will be equal to the amount of potential energy increase in melting plus the potential energy increase for evaporating. And so it's all law of conservation of energy. If I undergo an evaporation, there will be a specific increase in potential energy associated with that. And then if I undergo condensation, I will get the same decrease in energy coming back out, because now I'm forming new attractions. Questions about that? Overall, will the potential energy change be positive or negative if a sample of liquid undergoes evaporation and then that gas undergoes deposition? So if I have a liquid, it's going to undergo evaporation and then the gas undergoes deposition. Will the overall potential energy change be positive or negative? So I'm going from liquid to a gas. Then I'm going to do deposition and go to a solid. It'll be negative. Right? So I have to put some energy in to go from a liquid to a gas. Then if I go from a gas to a solid, I get the same amount of energy out plus a little bit more. So I have an overall release of energy, which from the point of view of the sample or system is always negative. So the potential energy change is often symbolized with the H for heat. Because if we want to increase the potential energy, we have to put heat in. If we form attractions and decrease the potential energy, heat will come out. So delta means there's a change happening. So delta H is the quantity of heat exchanged with the surroundings when a system undergoes some change in its state. So delta H of vaporization is the heat required to cause something to vaporize. Right, so if I want to take a liquid and make it a gas, I have to put energy in. So the sign for delta H of vaporization will always be positive. The quantity will be greater when I have stronger attractions to break. Right? Because to go from a liquid to a gas, the molecules in the liquid are closer together. They're sliding past one another, but they're still close enough together to form lots of attractions. So when I separate them, I have to break some attractions. I have to put some energy in to overcome those attractions. This is the quantity of energy per mole. So that means if I had a mole, or Avogadro's number of argon atoms, in the liquid state, I would need 6.3 kilojoules of energy to break all the attractions between that mole of atoms and convert it into a gas. Why is the heat of vaporization so much lower for argon than for most of these other ones? Yeah, argon is nonpolar. It's just one atom. It doesn't have any polarity. So this number represents how much energy I have to put in to break apart the attractions between argon atoms if I have a mole of those atoms. And since they're nonpolar and they only have weak London forces due to a temporarily shifting electron, they're only going to attract weakly. It's not going to take much energy to break them apart. So this is a very helpful number to have because it gives me a quantitative way to relate how strong attractions are between particles. And so I know, for example, that the attractions between ethanol molecules are stronger than the attractions between diethyl ether molecules because there's a higher heat of vaporization. It takes more energy to break the attractions and convert to a gas if I have a higher heat of vaporization. I can also look at the heat of fusion, which would be the melting process. So again, if I go from a solid to a liquid, I have to break attractions. If I want to break attractions, I have to put energy in. So heat of fusion is always going to be positive. It's the quantity of energy I have to put in to break some of these attractions. But do you expect heat of fusions to be larger or smaller than heat of vaporization? Would the heat necessary to get the molecules to just slide around a little bit and flow be more or less than the heat necessary to get them, that once they're already flowing, to completely separate? It's going to take more to separate them completely usually, right? So if we look at the heat of fusions, these are smaller numbers in general. And so if I have a solid, they're usually organized because they need to line up in a specific way to make the maximum number of attractions. So to break up that organization, get them to flow a little bit, I do need to break some attractions. This is the quantity of energy I need to break the attractions. Not all the attractions, just enough to give it flow and make it a liquid if I had a mole of a given substance. The melting point is the temperature at which I get an equilibrium between solid and liquid. And so if I have a solid, if it's below the melting point, the whole thing should be solidified. If it's above the melting point, it should be all liquid. But when I'm right at the melting point, then I have a situation where I have equal quantities of liquid and solid in the same container. Because, again, when you think about you're at a given temperature, some of the molecules are moving slower and some are moving faster, and they're colliding, and they're transferring their motion to one another. So a fast-moving molecule, it might collide with another molecule, transfer its energy to that other molecule. Like if you're playing pool, when you hit one ball into another ball, the other ball starts moving faster than the original ball did. So if this ball slows down because it's transferring its energy to another ball, and it comes in here on the surface and starts to feel an attraction, it will join and become part of the solid. And then if another one that's moving fast maybe comes in here and collides here, it might transfer its energy, and that will cause this one to start vibrating really fast. And if this one vibrates too fast, it might break its attractions and become then part of the liquid. So an equilibrium is formed when you're at just the right temperature and you have both processes happening at the same rate. So in a given period of time, I have an equal quantity of liquid becoming solid and an equal quantity of solid becoming liquid. So I have then no net change in the amount of solid or liquid if I'm at that temperature. Right, so when I reach that temperature for a solid and liquid, that's the melting point. Again, we can say something about how the melting point relates to the strength of the attractions as well. The lower the melting point, the weaker the attraction, because it doesn't take much energy to start to break those attractions and make it become a liquid. If I have a high melting point, I should also have a high heat of fusion because I have a much larger quantity of energy, much higher temperature necessary to get things moving fast enough to start to break the attractions in the solid. All right, so let's look at changes in both potential energy and kinetic energy as we go from one phase to another. So what we're going to do here is we're going to track this. So we're going to take a solid and we're going to increase the temperature. And we're going to look at heat changes for the substance. So what we're looking at here are potential energy changes for the substance. Right, so we've got a solid. We're going to heat it up. What happens to the solid? So we haven't changed into a liquid yet, still salt. So here we're comparing a sample of a solid at a low temperature versus a sample of a solid at a higher temperature. What happens to the particles in the solid when all I do is increase its temperature and I haven't started melting it yet? It vibrates more, it moves more, right? So that's expressed because from here to here, I have a temperature increase. That means I'm increasing the kinetic energy, right? Temperature is a measure of the average kinetic energy. So anytime I see the temperature go up, I know there's more motion, there's more kinetic energy. do I also have an increase in potential energy? Yeah, I do, because if the particles are vibrating more, even though they're still in the solid, they're still organized, they're still forming attractions, if they're vibrating more, the attractions are not quite as effective. So there's more potential for them to stick closer. If I were to take that vibration away, if I took the heat source away, they might kind of make a harder solid and get back into place and form better attractions. So I have a slight increase as well in potential energy. So if all I do is raise the temperature of something, I'm definitely increasing the kinetic energy, because that's what temperature measures, is kinetic energy. But if I make things move faster, I'll also make it harder for the attractions to hold it together. Right? That's why solids and liquids expand when you increase the temperature. Right? Because the particles move faster. That motion means that the attractions that are holding it together can't hold it quite as close. And so it expands a little bit. The distances get a little bit further apart. When I increase the distance between particles that attract, they're not as stable. There's more potential now for them to come back together. So if they're apart just a little bit, I've increased the potential energy a little bit. Okay, so this is going to be my melting point. So now I'm at the temperature where I'm at the melting point. So if I continue to put energy in, will the kinetic energy increase? I'm at the melting point now, so my particles are moving fast enough, they're vibrating enough where if I put any more energy in, they'll start to flow past one another. At this point, what actually happens is the next energy I add is all going to be expressed as potential energy. So what I see here is, once I get to the melting point and it starts to melt, any energy I put in is not causing a temperature increase. So during the melting process, I do not have an increase in kinetic energy. No change in temperature means no change in kinetic energy. But I'm still putting energy in the system. So what type of energy is it being expressed as? Potential energy. Right? So when I put this energy in, what is it doing? It's breaking the attractions, some of the attractions between the particles. So when the solid, they're lined up. Even if they're vibrating, maybe they expand, they move apart a little bit, but they're still lined up, they're still got those attractions. So if I start to melt it, if I put more energy in, it doesn't cause it to vibrate more. It doesn't cause it to move faster, because the temperature is not going up. If I keep putting energy in, once it starts to melt, the energy is only going into breaking the attraction, causing the particles to slide around. That is only an increase here on the x-axis. That's only an increase in potential energy, not an increase in temperature, not an increase in kinetic energy. So during the phase change, only the potential energy changes. Once now, if it takes this amount of potential energy to completely melt it, and once it's totally melted, now it's all liquid. Then if I put more energy in, the energy is both kinetic and potential. Right? So once it's totally melted, I keep putting energy in. The energy causes now the particles to move faster. So here again, I have an increase in kinetic energy and an increase in potential energy. Over here, I only had an increase in potential energy. So again, once I have a liquid, if I keep putting in energy, the particles will move faster and faster. Now they're not just vibrating, but they're rotating and sliding past one another and moving around. Putting more energy in, the temperature goes up. That tells me they're moving more. They have more average kinetic energy. But they also have a little bit more potential energy, because if they move faster and they bounce around and get apart a little bit more from one another, the liquid starts to expand a little bit, their attractions are not going to be quite as effective at holding it together. So then I reach the boiling point. Now I start to undergo another phase change. So what happens to the kinetic energy during a phase change? Nothing. once I get to the phase change, any energy I put in does not cause the molecules to move faster. That's why there's a boiling point for a totally pure substance. If I do it right, I get one temperature where the whole thing boils. When I get to the boiling point, the temperature doesn't change anymore. There's no change in the overall kinetic energy. I'm going from a liquid to a gas. In the liquid, at the boiling point, the molecules are moving around with the same average kinetic energy as the gas particles are moving around with at that same temperature. So the energy I put in once I get to the boiling point is all 100% potential energy increase. I need to put the potential energy in to break the attractions and separate the molecules. I'm not making them move faster because it's still at the same temperature. I'm just separating them from one another. So the energy is necessary to go into potential energy to get the attractions to break. Then if I have a gas, it's completely vaporized, it's all in the gas state. Then if I continue to increase the temperature, then the particles just express that as higher kinetic energy and higher potential energy indefinitely, as long as I continue to raise the temperature. Any questions about that? Okay, what has more kinetic energy? A solid or a liquid? What? Kinetic. What has more kinetic energy? A solid or a liquid? You can't answer. It totally depends on the temperature. Because the solid could be like 100 degrees Celsius and the liquid might be at 5 degrees Celsius. Then the solid would have way more kinetic energy, right? It's only the temperature that tells you the average kinetic energy. Right? So when you're thinking about the differences between the states of matter, you don't want to get stuck into thinking about it as one state of matter is moving more and the other state of matter is not moving as much. You want to think about just the differences between the states of matter are the differences in the strengths of attraction. In the solid, there's a lot more attractions holding it together. In the liquid, there are fewer attractions. So I can say that if I asked what has more potential energy, then I don't need to know the temperature. The liquid will have more potential energy than the solid because there's less attraction. Right? So potential energy is 100% based on how many attractions there are and how strong those attractions are. Kinetic energy is 100% based on the temperature. So if I make a change to my sample and the temperature is not changing, the kinetic energy is not changing. If I make a change to my sample and I have to break some attractions, then I know the potential energy is going up. If the temperature goes up, I know the kinetic energy is going up. Okay. All right, so sublimation is another possible change in the state of matter, and as we said, this is where it goes directly from a solid to a gas. Deposition is the opposite, where the gas converts back into a solid, and we talked about this a little bit last time. We said this happens for mostly large non-polar substances that involve large atoms like iodine, mirror to the bottom of the periodic table. It's got lots of electrons. The electrons can shift around readily. So a molecule of iodine is non-polar, but it's very polarizable, meaning the electrons in that molecule have the ability to shift and make it polar, for an instant, quite readily because there's so many electrons. And so it will create pretty big partial charges to attract the molecules together. That's why it forms a solid. They line up to maximize those attractions. Well, since the partial charges are temporary because really ultimately it's a non-polar molecule, if the electrons shift back to the point where they're not creating the charges anymore, then it will sublime. It will leave the solid because there's nothing to attract it, and it will be a gas. But then, after it's in a gas, if it's moving around fast or whatever, and it loses some of its energy, and it finds another molecule and forms that temporary partial charge again, and the molecules stick together, then I get deposition, and I see little specks of solid reforming directly from the gas. So I don't have any liquid present. I have solid going to gas and gas going back to solid. The amount of energy it takes to do sublimation is equal to the amount of energy it would have taken to melt it plus the amount of energy it takes to vaporize it. Law of conservation of energy. What's the relationship between delta H of sublimation and delta H of deposition? They should be the same value with opposite signs. Because sublimation requires the energy to be absorbed, deposition releases energy. All right, let's look at some of these questions in the book, make sure we've got full description of everything we need to know. 12.51, what can we learn about the intermolecular forces in a liquid from the molar heat of vaporization? So what that question is asking about, if we know delta H of vaporization, what does that tell us about the strength of attractions? Well, we know that the higher that value, the stronger the attractions. Right? That's because the heat of vaporization is the amount of energy I have to put in to break the attractions. So the more energy it takes must mean the attractions were stronger, better at holding it together. 1252, the greater the molar heat of vaporization of a liquid, the greater its vapor pressure. True or false? The greater the molar heat of vaporization, the greater the vapor pressure. Yeah, good. So vapor pressure, if you recall, you take an empty container, you take a solid, you allow the solid to melt into a liquid. Some of the liquid at a given temperature will evaporate and become gas. The vapor pressure is the pressure created by that gas colliding on the inside of the container. So if I have a greater heat of vaporization, that means it takes more energy to convert the liquid into a gas. So if I'm at a given temperature, if I have a greater, so at a given temperature, if I have a greater delta H of vaporization, that means I will have fewer moles of gas. If it takes more energy to break the liquid molecules apart and form the gas, then at a given temperature I won't have as much gas. I would have to raise the temperature higher to get more gas. So when I'm at a certain temperature, if the attractions are weak, then it'll just evaporate easily and I'll have a lot more gas. I'll create a greater vapor pressure. So weaker attractions result in a greater vapor pressure. Weaker attractions means you have a smaller heat of vaporization. 1254, a closed container of liquid pentane, boiling point 36.1 Celsius, is at room temperature. So room temperature is about 20 to 25 Celsius. So we're above, so the boiling point is above room temperature, but it is a liquid at room temperature. Why does the vapor pressure initially increase but eventually stop changing? So in this case, my liquid is pentane. Initially, the vapor pressure increases because initially I don't have any gas. Right? So initially, some of the liquid molecules that start moving faster than others will cause their attractions to the other liquid molecules to break, and they'll be evaporated. So the vapor pressure starts to go up. Why does the vapor pressure eventually stop changing? What? Yeah, I reach an equilibrium. So eventually, I get to a constant vapor pressure because the rate of evaporation of the particles into the gas becomes equal to the rate of condensation. And so as long as I keep a lid on it and I have enough vapor pentane then it will start to come back together and reform a liquid, and I will get that equilibrium to form. 1258. Why is solid carbon dioxide called dry ice? Because it sublimes. Because carbon dioxide is nonpolar, and so it doesn't have a permanently charged opposite charges on opposite ends. It doesn't have a dipole, but it can form a temporary dipole. So if I cool it down enough, the CO2 molecules will line up. Not because they have permanent partial charges that attract, but because they have temporary partial charges that attract. So one molecule creates some temporary partial charge, that and maybe induces the neighboring molecule to create some temporary partial charge, and then they attract and line up. That'd be in the solid. But again, since the charges are temporary, if then they shift back and create a nonpolar substance, it doesn't have attractions anymore. So instead of melting and being a liquid where there are still attractions, if the molecule doesn't have any attractions, it just floats away. And so it evaporates directly from the, or sublimes, I should say, directly from the surface of the solid. So that's why we don't have any melting of dry ice, it just sublimes. 62. A beaker of water is heated to boiling by a Bunsen burner. Would adding another burner raise the temperature of the boiling water? No, we just said that here. Once you're at the phase change temperature, until the phase change is done, the temperature will not change. So if I have boiling water, and I just increase the amount of heat underneath by adding another Bunsen burner or turning up the heat, the water is not going to change its temperature. It will boil faster. I'll get more water evaporating in a given period of time. But as long as there's still attractions between the water molecules, any energy I put in has to go into breaking those attractions before it can cause the molecules to move faster. So when I'm at the phase change, all the energy put in goes into potential energy, not kinetic energy, and so I don't see a temperature increase. 68. How is the rate of evaporation? How is the rate of evaporation of a liquid affected by some factors? Temperature. The temperature goes up, the rate of evaporation will go up. Right? You make the particles move faster, they'll be able to break their attractions more often, and they will more of the sample will evaporate in a given period of time. How is it affected by the surface area of the liquid? Well, if you increase the surface area of the liquid, the evaporation will happen faster, right? Because the evaporation can only happen on the surface. If a particle in the bulk of a liquid gets collided and starts to move faster and break its attractions, if it's in the middle of the liquid, it's just going to collide with something else and transfer that energy away and then slow down and start to reform attractions. Only the molecules on the surface, when they break their attractions, can really evaporate. So if you're just setting out a liquid and waiting for it to evaporate, it's going to happen a lot faster if you have more surface area. If you put the liquid in a container that's a wider container that creates more surface area for the liquid. And the last one here, intermolecular forces. Well, that one's easy. Right? The weaker the intermolecular forces, the faster the rate of evaporation. And if I have strong intermolecular forces, the rate of evaporation might be so slow, I don't observe anything vaporizing or evaporating. Right? That's what the word volatile means. Volatile means that evaporates at an observable rate at room temperature. And that only will occur if the strength of attraction between the particles is relatively weak. You could put a cup of water out on the counter. It'll be gone, depending on how much water you have, in a day or two. If you put a cup of oil out on the counter, you're not going to really see it disappear, because the oil molecules have more effective attractions between them.